Welcome back. Another day, and I'm in yet another hotel. This time, fast, reliable Wi-Fi. There shouldn't be any problems. I had to skip over day 8 because I was flying yesterday and didn't have the time, but I will just do 9 today, and then we'll see how much time I have, if I can go back and do 8, or... It's better to always do the day, the day that it is, instead of having them all start lagging. So we'll do day 9. All right. All right, that's everything. All right, let's start. Day 9. You slide down the fire pole. Okay. A wiki for fire pole. In the corner of the playground and land in the North Pole base movie theater. Excuse me. The movie theater has a big tiled floor with an interesting pattern. Elves here are redecorating the theater by switching out some of the square tiles in the big grid they form. Some of the tiles are red. The elves would like to find the largest rectangle that uses red tiles for 2 of its opposite corners. They even have a list of where the red tiles are located in the grid. You could choose any 2 red tiles as the... Okay. We're choosing 2 red tiles amongst all the pairs of red tiles. We want the largest rectangle. Alright. I mean, that's... How big is this map we're talking about? That's... Okay, we can do that with like a double for loop. I mean, we just iterate over all the red tiles. So... Let's do that then. Nine. So... Alright. We want reds equals, let's say it's a set. And we should put this, just put that there. Alright, so for each line, so it's... It's XY coordinates, right? Or doesn't actually matter. Doesn't actually specify. It doesn't matter though. Alright, so just say ij equals int x for x in line dot split on the comma. Reds dot add ij. Reds dot add. Oh yeah, I always, yeah. All right, that is a set. Not that was the other thing was dictionary. All right. So we want to do, let's say, best area equals 0. And what do they want? Just the area. What is the largest area of any rectangle? Okay. This is one of the easiest part ones yet. I mean, how many are we talking? 496? Yeah, so we can just... For P1 in reds. For P2 in reds. It doesn't even matter if they're the same. If so, area equals alright, let's just I1, we'll just do it like this. For I1 J1 in reds, for I2 J2 in reds, area equals absolute value of I2 minus 1 times absolute value of J2 minus J1. Best area equals max of... So just do it like this. Best area equals max of best area map. Print best area. That. It's wrong. I said it was the easiest part one, but I got it wrong, so... Just area. Oh, because it... Oh. Because you have to add one. You have to add one to it because it's including, how do I explain it? It's the outer rectangle that goes around it. So like, for example, hello Amaro, this one, my calculation will give 0, but it's actually, you add 1 to each dimension. Okay, so I just need to fix that. Did you do 8? I didn't have time yesterday, so I'll have to catch up on that. Possibly today, if this is an easy problem. So you add 1 here. Add 1 here. Okay, try that. We're probably going to be timed out. Okay, that's correct. Part 2. The elves just remembered they can only switch out tiles that are red or green. So your rectangle can only include red or green tiles. In your list, every red tile is connected to the red tile before and after it by a straight line of green tiles. The list wraps, so the first red tile is also connected to the last red tile. Tiles that are adjacent in your list will always be on either the same row or the same column. So we've got line segments of green, essentially. All right. In addition, all of the tiles inside this loop of red and green tiles are also green. Oh, it's one of these problems. Okay, fine. Okay. The remaining tiles are never red nor green. The rectangle you choose still must have red tiles in opposite corners, but any other tiles it includes must now be red or green. So it must be basically like convex subset something or other of this. Alright. Fine. This significantly limits your options. For example, you can make a rectangle out of red and green tiles with an area of... Alright. Okay, that's an interesting problem. And the numbers we're talking about here are... I mean, you don't need to store every individual green tile, you just need the line segments. These are pretty big numbers. So... So essentially, if you are given a rectangle and you want to see if it lies inside this shape, you're doing a line intersection check for each of the sides of the rectangle, right? You just want to check that it doesn't cross over a boundary. So that's the first check. So you know it doesn't cross from inside to outside or vice versa. But then you have to prove it's fully inside. So in that case, you do what, a point in polygon test. So you take a point arbitrarily inside the rectangle, and you drop a ray vertically or whatever. You count how many times. See, this is that might be a bit excessive though. We can work out at some point where the inside and where the outside is. All right. I mean, I just said it, didn't I? I just said what the solution is. I'm just... something's making me hesitate. That should just work. Well, the point in polygon test isn't going to be that long because we don't have to do drop the ray cell by cell. We just check how many lines it intersects, so it would be like a for loop through all the lines. Which we've got about 500 of them. That's not too bad. So ultimately, this is mostly linear time. It's not actually quadratic or anything. And quadratic would be fine as well. All right, I think this is fine. All right, let me try and put this into code. So, okay, so it's we want to store the line segments. So let's call this corners. It's a more clear definition. Because the colors don't actually matter. Like the greens, we can just assume they're part of the shape, but we need to know the corners, and we need to know the edges. And the edges go from corner to corner. Okay. So we want edges equals it doesn't need to be a set. Just make it a list. Edges is a list as well. So we've got the corners, we've extracted the corners, and now outside of this width, this loop, we can just compute the edges. So for I in range, so for I, or iter, corner in corners. Enumerate corners. Oh, there's a thing called iter. It then. So an edge is basically a pair of corners. So we'll say what happens if... There's some interesting situations we can have here. We can have a space-filling curve where you could have lines that kind of fill a space so that you technically... your point in polygon test might return that you're outside. However, the lines fill the space, so it's as if you were inside. Like, would they do something cruel like that? Maybe. In which case we would need to check... God, what would we do? Like, we basically just never want any point in the rectangle to be in the outside. And... one second. Alright, oh, okay, there's a few issues that come up here. Alright. Hello, DJ. Playing with polygons. It's a tricky one. The solution I described, it could work, but I'm trying to think of a... Like, there's definitely edge cases that he could... Literally edge cases where he just has a lot of edges. close together to form a block of red or green colors. And then... Alright, what can I do right now? Well, let's store the edges. So we've got corners. So each pair of corners, there's an edge between them. Edge. If it's the last corner, edges dot append corner, and the next corner is 0. The first one. So the last corner pairs up with the first corner. Corner's 0. Else it's just like I could have done that using modular arithmetic, but I'd rather do it like this so it's clear. It's just more readable. That these are two different cases. All right. Print edges. I want to see what this looks like. Okay. So that's the list of edges. Oh man. Alright, so part 2. So we said we want to do the same as before, try all pairs of corners. But for each pair we need to double check. Alright, so let's just write this. So we can say best area 0. Okay. So for each we now have a rectangle. So what is the first thing we want to rule out? Ultimately, we're trying to find if there's any outside space in this rectangle. For that to happen, so we know this rectangle collides with an edge because it's literally starting on an edge and finishing on an edge. The corners are on edges. So for every edge that crosses this rectangle, we need to confirm that there's no like... Find this. Um, I'm thinking about too many different things now. All right. Okay, what did I say? I said if for every edge. Okay, for a given edge, we can work out which side of it is outside and which side of it is inside. Like we can store that from the start. Like, okay, so this is a directed edge list. It's going like in one direction, and it might be going clockwise, it might be going anti-clockwise. So we have to decide that now. So now that we have the edge list, we need to figure out which side is the outside. Like, we just need to figure out if we're going clockwise or anti-clockwise. How do we do that? It's a winding number thingy. It's like... Excuse me. Oh, either... Oh. So either we count how many times we turn left and turn right, and that number tells us wait, can these edges intersect with themselves? Probably. Let me read this again. Nothing forbids that, so they could be an intersecting line, self-intersecting. I hope it's not, but... Okay. We just find the edge that is left, the vertical edge, which is leftmost. Right? And any space to the left of is outside. And that immediately tells us whether it's clockwise or anti-clockwise. So let's do that. So we take... leftmost equals none. For edge in, I don't know, let's say for P1, P2 in edges, if so we're taking I to be... So we want it to be vertical. So the J values should be the same. So if P1 1 is P2 1, so it's a vertical line. And if leftmost is none, or P1 1 is strictly less than whatever we currently have, so leftmost, just pick one of the two points and then pick its J value. It would have been clearer if I used pauses here. Maybe I should. It's not too late. Yeah, I probably should, shouldn't I? Pause. Where did we write pause? rewrite this using this. Alright, we'll use X's and Y's. Alright, so... Okay. So, for t-coordinate in numeric corners... So corners, that's fine. Alright, print edges, and then here we want if p1 dot x is p2 dot x. Then leftmost equals P1, P2. Alright, do that. So at this point we should have the leftmost. Let's print it. I just want to see what this looks like. Oh, this is going to break because we haven't done this down here. So it's going to be p2 dot x minus p1 dot x, p2 dot y minus p1 dot y. Okay, let's take this out for oh, whatever. No, just take it out. Name z is not defined for z. Okay, so using pauses now. That makes things cleaner. Right, so then we've got the leftmost, which is this. This is the leftmost edge. So what does that tell us? This tells us, so because it's going down, this tells us that the outside is to our right and the inside is to our left when we're walking along this directed edge. And that will therefore be the case for every edge in the list, because it's a continuous list. It's a continuous walk through the edges. So how do we process that? We want to say we want to say if leftmost one dot y is bigger than leftmost 0 dot y. That means this line is going up. Then what is it? What do we want? A Boolean? That's a weirdly named Boolean. I can't think of anything else. Outside left, it means on any edge in this list, if I put my hand to the left, my hand is outside. Unless, of course, there's another edge coming the other way. I don't know. The outside is to the left of me. Right. That's what we wanted to know. So with that knowledge, we now know where the outside is for every edge. Does that help us now? So we now have a rectangle. We know that it touches two corners, therefore it does intersect with edges. Let's also say if P2 is P1. Continue. Oh, this is part 1. Okay, that's fine. Let's copy this. Part 2. Alright. So now let's think. So we have a rectangle. We know the Is it enough to simply take each edge of this rectangle, check if it if we walk along the edges of the rectangle, and if every individual step stays in the shape, and if we do that all around the rectangle and manage to get back to the beginning, and we never left the shape, then that proves we're inside, right? There cannot be an outside space within that rectangle, because by definition, outside is one continuous unbounded connected space as defined by the Jordan curve theorem. So basically the problem is these numbers are really big, so it might not be too bad actually. Okay, so here's the plan. We walk around the rectangle just step by step. There's probably quicker ways of doing this. I think the quick way of doing this is checking, instead of going step by step, you want to just check I don't know. Wait, what would... Like, how big are these edges? Can we just... define... Hello, Slinky. Here we are a year later and still not using Rust. I mean, Python is by far the best language for advent of code. There's so many times where I'm so glad I used Python. Parsing, using eval sometimes comes up. Unbounded integers. Sometimes you have to add integers which are like 100 digits long. Alright, I'm wondering if we can just basically add... Can we just define a set of all points on all the edges? Like, are these small enough that we can just do that? Let's try that. If we just know the full boundary definition of the boundary, then it's easy. We can just walk around the rectangle, check if we ever cross boundaries. Okay, let's try this. So I need, okay, you know what? We need to whip out the big guns. We need Microsoft Paint. Oh, I had a capture for this. Let me... I'm not gonna have time to go back and do day 8 today, so I'll have to Maze is so... Hang on. Okay. Oh. Okay, before I switch to paint, let's make it dark mode. Fill it black. Brown or something. Red. Alright, fine. Don't want to blind anyone. Okay. There we go. Oh. Can we... Hang on. There we go. Alright, what am I trying to do here? So, let's say we've got this weird shape. It could self-intersect. I assume not, but they never strictly said anything about that. So, it can wind around, but eventually it reaches the beginning. So what we did is we took the leftmost edge and we said, because there's a direction we walk around this. So we always know that either if we put our left hand out, we're in the outside, or we put our right hand out and we're in the outside. So to do that, we take the leftmost edge and check whether we're going up or down. And if we're going up, then we say, okay, our left hand is outside. And if we're going down, we say, okay, our left hand is inside. That defines which side is the outside. That's important. So now what we're doing is we're trying to take every pair of corners here. So let's say this corner and this corner. And draw a rectangle which meets those corners. And we're saying, is this rectangle fully inside? And so what I want to do is I want to say, well, okay, these two corners we know are on the boundary. So if we were to walk around this rectangle, every step we take, if we leave a boundary, we may stay on the boundary, or we may leave the boundary. If we leave the boundary, we need to check if we go outside or inside. And if we step onto a boundary, that's fine. But every time we step off a boundary, we need to check if we've gone outside or inside. And we know every time, because we know which side is outside and which side is inside, because we've stored that boolean. So putting this all together, what we're trying to do is for each of these each side of the rectangle, we basically want to check which edges it intersects with. Okay, so we need a method which checks for intersections. So if we magnify that, we say we've got this rectangle. Okay. For this edge, we want to find all edges which cross it. All edges of the original shape, the big shape which cross it. So there may be some edges that go like this, maybe some edges which are vertical. And for each of those, I guess we need to evaluate, like, see, if you ever have an edge going perpendicular, you would probably, that probably means we've stepped outside, right? Because either this side is outside or this side is outside. But that's not strictly true. And I'm hoping this doesn't come up. But in theory, you could do an edge going like that, and then you could do an edge going like that, and you could do an edge going like that. You basically have a space-filling curve, which means you can actually cross edges without ever going outside because you're just hopping edge to edge. And I don't know if he'd actually do something as extreme as that, but then maybe he will. So the reason I have to do such a complicated algorithm here is because of that scenario. It's not strictly true that an edge crossing perpendicular proves that you're stepping outside. Because one side is the inside, one side is the outside. Unless you've got edges all the way down. So I think what we got to do is for every edge that crosses horizontally, or perpendicular, I mean, we've got to check the step just here. We've got to check the step just here. Is either of those outside? That's what we got to do, right? It seems complicated, but I mean, this is to deal with this weird case that I've come up with here that I think you have to. All right. And what if it's not, what if it's a parallel, not parallel edge? Then that's an easier thing to deal with, but we just need to check we still need to check that point there. So if this is our rectangle and this is an edge, I can't draw this properly. This is an edge it intersects with, then we need to check this point here, and we need to check this point here. Just to check we haven't stepped outside. All right. I don't know. Let's try coding something. So we need a method to check if two lines intersect and returns the intersection. Basically, a line segment, which is the intersection between those two. It may be a point, it may be a line. So we should return a line, because a point is a line, which just kind of drops on itself. So let's write that. Define get intersection of lines. So it'll be line 1, line 2. So P1, Q1, equals line 1. P2, Q2 is line 2. This, I can't be bothered to write this. Can we find this? Let's see if there's a nice clean Python method for this online somewhere. Python method to compute line segment. Because it's just going to be a lot of case checking between two line segments. It's more complicated than I thought it was. Alright, well, I just want to use some pre-written code. I don't need to go back to the geometry of line segments. Oh, this isn't visible on screen. I'm just looking at different line intersection methods. God, it's actually quite complicated. But it's always it's assuming we're not dealing with just vertical and horizontal lines. It's actually much simpler. Okay, maybe we just write it ourselves then. Okay. If line if P1 dot X Alright, if it's vertical, we say P1.x is Q1.x and P2 so they're both vertical. Then if P1 dot y is P2 dot y, then we've got two lines which intersect. So that the top of this line is going to be the minimum of P1 dot oh, this is so confusing. P1 dot y, Q1 dot y, 2 dot y, P2 dot y, Q2 dot y. So it's min-max to get the top and the bottom of the line. And then we return top, bottom. We return the line segment, which is the intersection between the two. Else return none, because there's no intersection. And then we have to do the same thing if they're horizontal, I suppose. So it's P bond dot y. What's the y? Okay, so they're both horizontal. So we should just change every x to y and vice versa. And top would actually be right, left, so be left, right. Okay. So that's those cases, and then so that's if it's horizontal, that's if they're both the same. Otherwise, they're perpendicular. How do you check if two perpendicular line segments cross? Check if two perpendicular line segments intersect. So use the cross product or something, don't you? Stuck? No, I'm trying to solve the problem. Let's check all these solutions are very complicated because they're not assuming they are. Oh god, this is huge. But that's how you check. That's how you check if lines intersect. You have to do all that orientation and collinear stuff. I could just copy it in. It's so complicated to check if two lines cross. Wait, why couldn't we just check if the infinite lines cross and then check if those are on the line segments? Wouldn't that be easier? Yep, no, that's what this formula already does. It's just really complicated. Alright, well maybe I just copy it in. Okay, here's a method. Let's form Stack Overflow. Let's use this one. It uses matrix algebra, whatever, determinants. Line intersection. We need to be clear that this is just getting get point intersection. Points. Oh, but it's okay. Now we need to change this also to X. So determinant is that line determinant. If it's 0, raise exception lines do not intersect. Sure. Then we return none. Otherwise, we do that, return. x, y. Alright, let's hope this formula works. So now we do else return get pointer 6 and off line 1, line 2. Let's test this out then. So let's say line 1 equals, so it's going to be pause, let's say 0, 0, pause, 0, 10. On line 2, will be, I don't know, 2 and 8. So I want to see if we get like we want to get intersection of these two lines. We want to get a line segment. Alright, see what happens. We get none. If and stop printing all these things. We get none. 0, 0, 0, 10, 0, 2, 0, 8. These are both vertical lines. Oh, they should intersect. So we should fall into this case. They're both vertical. P1.y equals... Wait, no. Why is that y value? That should be x. That should be y. Okay, 8, 2. Alright. Looks like... Ah, wait, no, we're not done here. Hang on, top is the y value. So it should be... Pause... P1.x top. Pause... P1.x bottom. Okay, 0, 8, 0, 2, 0, 8, 0, 2. Okay, that's the intersection between those two. And if I change this to be like on the 1 instead. No. Okay, and now let's do, let's say this is 0, minus 10, 10, and then this would be the 0. We can do like -5 and +5. So we should intersect at 0, 0. Fake. Oh. D equals det of line 1 det of AB. Okay. We have to redefine this. Xdiff. God, how complicated is it to check if two lines cross? Xdiff. Why is... What is this? That's not a vector. What is this? Alright, well, we can't do this, whatever that's doing. We need to... change that to say... line 1 0 dot x basically do that. Okay. 0 0. Okay. Fine. We're getting somewhere. We now can find when two lines cross. And it took that much work to do. Alright, well. Hopefully that method works now. Alright, so back to the problem. What were we trying to do? We want to see... For each line of the rectangle... Alright, let's start by listing the lines of the rectangle. So, P1, P2, other corners. So rectangle lines equals, so we've got P1 well, let's say rectangle corners equals so we've got pos of P1 dot X paired with P2 dot Y. We've got pos of P1 dot P2 dot X paired with P1 dot Y. So we don't need that line. We just need to say for rect edge in. So we've got P1, and then we've got that. And then we've got P1 going to the other one. And then we've got P2 going to one of these. And finally, P2 going to the other one. So those are the four edges of the rectangle. We don't need that line. Or rect edge in that. Alright. For edge in edges. So that's like 500 different edges we're trying. So we've got a rect edge. We've got those are edges. Intersection equals get intersection of lines, rect edge with edge. Now, if intersection is none, continue. Alright, so that's fine. That edge does not intersect. If it does, we've got two cases. Either they intersect on a point, if it's a point, it will look like a pause. All right. if type intersection is pos. It's the intersection of a point. What are we trying to do now? We're just trying to see if either point either side is an outside. So the neighboring points. How do we... Okay, I just need to check if it's vertical. I can't... We need a vertical check. So that I don't have to keep writing this. I've done this multiple times already. Let's define... Define is vertical line. And to do that we say if line 0.x is line 1.x, let's just return that. So where did we do this? Here somewhere. If is vertical if is vertical line 1 and is vertical line 2. Right, and then we want if not is vertical line 1 and not is vertical line 2. Alright. And down here, okay, if is vertical rect edge, then neighbors equals intersection plus a delta in the y direction. Or just say for delta in, so we've got pos 0, 1, pos 0, 2, we'll just say deltas equals that, all right, and that's not even right, that should be -1, else it's going to be -1, 0, 1, 0. Okay, so we're just saying what the neighbor points are. And the point is... God. Now what? This is all to cover this ridiculous case that I bet doesn't even come up anyway, but I'm trying to make my code fully correct here. So what we're trying to do, so we're crossing an edge, And we know that one of the sides of this is outside. So we know we're already breaking the rule. We're going outside. However, that outside point might be covered by a line, in which case it's not actually outside. So we want to check if... so we know strictly one of these is inside, one of these is outside, because we're crossing a edge. And that's how it works when you cross an edge. One side is inside, one side is outside. We want to check... We want to check which one's... God, it's so confusing. Oh, so much geometry and algebra in this. How do we... Alright. What we need to do is we need to drop a line going from the start of this edge up to this intersection point and turn left. No, not even left. We turn whatever this variable says. If it's true, then we turn left. If it's false, we turn right. Okay, fine. We don't even need this. So... Use 1.5 hours so far. Okay, so... Okay, this for loop is getting too big. Let's just make a method here. Define is rectangle inside. And we're given 2 corners of the rectangle. So for P1, for P2, we want to basically take this out. If the intersection is a... You know what? I've just realized we don't actually care about them being parallel. If they're parallel, then this is no not an issue. So we can actually remove a bunch of code from that. So we don't need... Okay, if type intersection is pos, we don't need to do the if it's a vector. We don't need to do the other case, just do this case. Alright, so let's assume that method is written, and we say if is rectangle inside P1, P2, then we just do the best area calculation we did before. Okay, so it all relies on finishing this off now. And if we get to the end of this loop and we never found an outside space, then we return true. So the moment we find an outside space, we return false. All right. Okay. So we want the vector from edge 0 up to the intersection. All right. And that is going to be a vertical or horizontal line. All right, this is what we're doing here. So we've got a line, and we know one side is outside, right? And we've got this intersection point here. So we're saying if we walk along this line, and I know that outside is always on my left, then we're talking about this space just to the left here. And we want to check if that's covered. So what we need is the vector. Oops. And then we need to scale it down so it's like a unit vector. So how do we do that? We say let's just make a unit vector method. So if vec.x is 0, then we return pos 0, and then it's going to be 1 if vec.y is greater than 0, else minus 1. Else elif. What if it's... we shouldn't have 0 length edges. Oh, we can. let's hope that doesn't happen. No, it shouldn't happen because, alright. Missing return statement on some parts, yeah. It's fine. Alright, so here we say vec equals get unit vector edge 0 to edge 1. So that gives us the unit vector. Then what, we want to rotate left or rotate right? God, now we need a method for rotating a vector. Define rotate vector. I gotta look, just Google this. Python method to rotate vector by 90 degrees. It's gonna be you can use NumPy for this, but I don't want to rotate. Okay, it's like this basically. So it'd be vec.y minus vec.x. So this is what, clockwise? Like that. And then if we want anti-clockwise, it'll be so it'll just be the same, but we wanted to so be minus and just plus there, right? No. Yeah. I'm just spending all my time writing the most basic helper methods that you're supposed to just kind of... Normally you'd have all these ready in like any kind of... NumPy probably has them all already. I should have just used NumPy. Okay. So. Almost there. So we get as far as here. Now we say... If... So... What was the variable we were looking at before? If... outside left equals true. Okay. If outside left. Outside point equals. So we're gonna rotate this vector to the left. So we do rotate vector anti-clockwise of the vec. So that gets delta, and then add that to the intersection. Else, it's just clockwise. Alright, what is the point of this? We've now got a point which we think should be outside. But, as I said, if we have a weird scenario where we have a space-filling curve or something, it could actually still be inside because it's on the edge. So... this is what we need the boundary for. Can we do this in a reasonable amount of time? Yeah, we can. We absolutely can. Right, let's do that. So, okay, so we've defined corners, we've defined edges. And now one last thing we want to do is define boundary. So... okay, now boundary equals set for edge in edges. So we've got 2 points, and we want to say everything in between is on the boundary. So if is vertical, P1, P2, if it's vertical, then for y in range, starting from okay, minimum of p1 dot y, p2 dot y, and ending on maximum of p1 dot y, p2 dot y, inclusive. Boundary dot add, so it's going to be a position. P1 dot x and y. Else we have to do it like the other way around. So for x in range, minimum p dot x plus 1, boundary dot add x, p1 dot y. Y. Okay, will that run in a reasonable amount of time? Also, this does floating point numbers. Can we not do that? Can we let's make sure that ends. Unit vector, get unit vector to get unit vector, so it should be, we should just give it the edge, shouldn't we? Tuple has no attribute x. What is this? This is a pair of points. What? Why was I doing this? No, it's if vec 0 dot x let's say if is vertical vec else. Okay. Tuple has no attribute X. What? Why did I do this? What? One if... Ah. Vec 1.y minus vec 0.y is greater than 0. Okay, it runs, but how much is it computed? We're stuck in some loop here. Did it compute the boundary? Well, we did part 1. Here is where we're taking all the time. Let's just finish off the logic then, and then figure things out. So, outside left. Alright. Almost there. Now we need another method. We need a method to check if a point is on a line. Python method to check if point is on horizontal or vertical line. So either it's oh, just write it. So if is vertical line, return e dot x equals 9x and sake, because now we need to go. Okay, right, fine. Minimum of line zero dot y line 0.1 dot y is less than or equal to p dot y is equal to max else, so it's that and a y next time I'm using a geometry library for this is all like primitive stuff. We shouldn't be having to do all this. Okay, that's to check if a point is on a line. Okay, here's the big logic. If outside point, so let's say is point on line, outside point is on the rectangle's edge and not outside point in boundary, then we've just proved that this rectangle dips into the outside, because this is a point that's on the rectangle's edge and it lies outside. Now, in theory, this should just work now, but it's probably going to take too long. Let's get some measure of progress here. Four. Four. P1 equals print P1. I don't know. Okay. Alright, we're getting through them. It's just gonna take a while. It's probably gonna give us the wrong answer. This has not been a This has not really been a good day for me to do it anyway. I'm pretty tired and I don't have time to do day 8 today, so maybe I should just come back tomorrow with a fresh mindset and more time. I don't know. Let's see. Well, 92916. Try it, but I think there's so much that can go wrong here. And it seems very few of these no, it's too low. Fuck. Largest area of any rectangle you can make using only red and green tiles. At least we know it runs in time. It's just a question of getting the right logic now. Okay, so let's try the test example then. So the correct answer was 24. And we got 12? It's like half. Interesting. So the correct answer for the first part was 50. So let's print Amara, well, I wrote a whole bunch of geometry pulper methods, which was a pain, and that took up most of the time. Like checking if a point is on a line, checking if a line's vertical, stuff like that. I should have just used a geometry library. Like NumPy probably does all this anyway. Probably should just use NumPy. I've written what I thought would work, but I know that there's probably something wrong with it. Testing it on the test example now. So the bulk of it is this method is rectangle inside, and we're trying to check if it's inside the space, and it's a bit of a mess. I think I checked for a line going from one end to another. Check. Checked what? Essentially what I'm trying to do is for the rectangle in question, for each of its edges, I want to look at all the, let's call it the polygon, this shape, whatever it is, all the edges of the polygon that intersect with it. I just want to look like either side of that line, because we know one side is the outside, one side is the inside. So I look at the outside side of that line. I want to see if that outside bit is on this rectangle's edge and is not red or green. Ultimately, that would prove that that is an outside point which is on the edge of this rectangle. Therefore, this rectangle dips outside. That's what I'm trying to do. Because if there's an outside point somewhere in the rectangle, then it's necessarily the case that there's also an outside point somewhere on the edge. So you need only check the rectangle's edges. So basically, I'm checking the rectangle's edges to see if there's any outside points. Right now we're getting, so for the test example, I'm getting exactly half of the correct value. Let's have a look, see what's happened here. Let's try that. So we did 7325. And they're saying you can do better with 9523. Interesting. Nine, 5, 2, 3 is what? This rectangle here. So What? See, that's quite a nice shape. What? It's not weird in any way. Why did that not work? So our algorithm is claiming this rectangle lies outside. So it's found an outside point somewhere on the edge of this rectangle. So let's print what that point is. And then we'll figure out why it was mistaken. So print print P1, P2, outside point. Let's just see what it says. So, also stop printing so many things. Let's take that out. Okay. So we want to check 9.5. Nine 5 2 3. Also, we're doing. No, it doesn't matter. 9 5. Here we go. 9 5 2 3. So we're saying position 8. X equals 8. Y equals 3. Is an outside point. 8 3. Okay. Interesting. So 9 0 1 2 0 1 2. Wait, these are not. That's 2 3. That's 9 5. Basically, I checked for green lines. And so this is 2 3. We're looking for 8 3. So that's 3 3 4 3 5 3 6 3 7 3 8 3. So for some reason our algorithm says that is an outside point right there. Our algorithm thinks that is an outside point, so it's saying this line here this is a directional issue. Have I maybe I flipped a line around at some point? So we know that we've got a direction of each of these lines, and it goes around in like clockwise or anti-clockwise or something. So we know always that the outside is on our left, or the outside is always on our right, or something like that. Maybe I've flipped it at some point. Did I put the edges in the correct order? It's always from one corner to the next, and in this case it's the last corner matches to the first, and then this one to the next. Okay. So... yeah, the edges in the right order. So if outside left... so we're looking at the leftmost edge. We're saying... so we think false. So we think the outside is on our right as we walk around this. Let's check if that's true. So we go from 7-1 to 11-1. There's no... 7-1 is which one? Seven one. Is that 7, 10, 11? This edge here, going from this point to that point. 7, yeah, okay, 7, 8, 9, 10, 11. So we're saying false, which means we think the outside is, well, right. We've got it completely wrong. How did that happen? Hello, Peddler Stories. So we've literally got the opposite of correct here. False. So we're saying the outside is to our right, but it's very clearly to our left. How did that happen? Let's have a look at this again. P1, P2. If, so why did I do this? If okay, make sure we're saying is vertical. Use is vertical whenever we can. All right. P1, P2. So it's a vertical line. P1. Oh. No, that's fine. So this just takes the leftmost edge, which should be just the edge on the leftmost. And then we look at this edge and we say, if the second value is higher than the first, then we are going up. And therefore the outside is on our left, because there's no more edges to the left of us. That's correct, isn't it? How did we get this the other way around? But we get false here. Okay, so we're saying 2, 5, 2, 3 false. 2, 5, 2, 3 false. So 2, 5 is what? This edge 2. That's 2, 5, and that's 2, 3. No, or 2. What? Oh, because they're doing it y increasing in the other direction. But okay, we were using Cartesian coordinates, so it shouldn't really matter. It's just flip. Hang on. It won't actually matter. It doesn't matter whether it's flipped or whatever. So, but it seems they're doing y increases in the downwards direction. It'd be nice if they actually made that clear, because they're giving us a diagram. Alright, well, we're saying the leftmost edge is... Right, this diagram doesn't help them, because it's actually flipped or something, I don't know. So just work with the code. We're saying that if the leftmost edge goes from 2, 5... which is up here, down to 2, 3. And this is the leftmost edge. That means the outside should be to our right as we're going from that point to that point. The outside should be to our right. So false is the correct answer here. Had a lot of trouble with day 8. Ended up settling for a 5-minute compile. Oh, okay. Compile? Alright. You mean compile and run? So this still looks correct to me, so why have we... What would happen if I just flipped this? Because apparently we've got the wrong Boolean here, even though I thought it should be correct. What happens if we flip it? 8. We get an even worse answer. Okay. Fine. Hello, Fernif, Sigma. Okay, we're gonna have to... Okay, so this... I've been led astray by the diagram, because the diagram is not... It's not representative of the way we're doing it. We're doing it with Cartesian coordinates, and they're doing it with, like, computer graphics coordinates, whatever. So, that's what's throwing me off. So, we are saying... So they say that the best area you can get is 9523. And when we try 9523 here, we say this rectangle dips outside. And we say that because this point here is on the rectangle and it's outside, which we know is wrong. What is the challenge today? I can post the problem. There. That's the problem. Although if you haven't completed part 1, I don't think you'll be able to see part 2 on that site. I don't think I can go on for much longer today. I might have to leave this and problem 8 for tomorrow. So we're going to be way behind. Okay, this is probably not too hard to debug then, because we've explicitly said something very, very wrong here, that line there. It's saying that this rectangle, even though this is a big rectangle and it's size 24, and that should be the right answer, that should be the biggest rectangle, we're saying it violates the rules by having a point outside. And we know that's not outside, so we just have to find out how it ended up outside, and it's probably just something got flipped or something. So like, we're saying that that point is on the rectangle's edge, which I agree with, that it is on the rectangle's edge, and it's not on the boundary. Which I agree with. It's not on the boundary. So that we agree with that statement there, but we shouldn't have got to that point. So what I don't agree with is that that point is outside. Interesting. Did I get my clockwise, anti-clockwise correct here? Oh, I don't know. So I'm saying that's rotating clockwise and that's rotating anti-clockwise. So for this shape, we know that whenever you put your hand out to the right, you're outside. That's what we've decided, and that's correct. We've decided for this particular shape, the outside is to the right. So for that particular edge, Let me just print the edge. Because I'm getting confused here. What's the edge that we're talking about here? 9523. Okay, 9523. Okay, so this line here. The edge is 97 to 95. So it's going down. Therefore, everything to our right is outside. So 8-3. I think the problem is actually this boundary checking then. So I think that's actually computing the correct right-hand rule. It's found the outside point, it thinks it's outside, but it's not accounting for the fact that that is actually lying on a different edge's boundary. So maybe I just didn't compute the boundary correctly. Boundary. Let's print the boundary then. 8-3. Print boundary. Is it like empty or something? What's happened here? F10. Where's the boundary? That's the boundary. Eight, 3. Oh, I can't. This diagram is confusing because it's the wrong way around. Alright, so we're saying 8-3. We're just going to have to do our own diagram. So 8-3. Should not be on the boundary. Alright, I might leave this for tomorrow because I'm trying to do too much in my head. Clearly we need to actually print this out, write the coordinates down, check each of these things is correct. And if I can just debug that one line, that's probably the source of the issue. So that could be all that's wrong with it. I don't know. But I can't do it now. I don't have time and I'm pretty tired and tomorrow will be a better day for it. That means I'll be 2 days behind tomorrow. That's not good. I'll just have to try and put in lots of time to finish it all off. Well, that's what happens when you have a boat followed by a flight on the same day. And then I'll get on to day 8, which apparently is harder. I mean, I think what I've done is not actually that complex now that apart from the fact that I had to do a million different helper methods for all the geometries of point on a line and line intersection and all that stuff. But conceptually, all I'm trying to say is, really is, if the rectangle, so it's like basically from here to here, I think. So that rectangle crosses this line here. And this line here has an outside point, which is like, should be here. So that line thinks that point is outside. But obviously it doesn't know that there's another line which that point lies on, which is not outside. But from this line's perspective, it thinks that's the outside, that's the inside. So on our rectangle, we cross that line. So it remains to look at that point, which we think might be outside, and check whether it really is outside. If it lies on some other line, then it's not, and we're safe. What's with the sad emoji? You wanted to see me finish? I spent a long time writing a lot of geometry methods, so that slowed me down. I should have just used NumPy. I mean, it's not too late to switch to NumPy. I think NumPy just does all this stuff. Or Sippy or something. And the whole reason I'm doing this overly complicated way of doing it is because there is a weird edge case that I think could be, in theory, be in the input, but I wouldn't be surprised if it's not. Maybe he's just given a really nice input, where you can just have a space-filling set of edges which go back and forth like this, right? So you could have a rectangle which is completely covered by edges, and that means it's inside, even though it's actually just sitting on a bunch of edges, all of which think you're crossing to the outside, but every time you cross to the outside, you're actually just sitting on some other edge. So this is like a space-filled curve, essentially. So it's actually inside, because it's on a bunch of edges. So that's why we need to do this outside check on an edge per edge by edge basis. Anyway. But in reality, I bet the input's just a nice spaced out, non-self-intersecting polygon. Yeah, they never said, they never even, oh. Oh. Could that be the problem? Yeah, but no, the test example is non-self-intersecting, isn't it? Could my assumption of outside versus inside be thrown off by the fact that the curve is self-intersecting? But I don't think it's self-intersecting, but they never said. But for the test example, it's definitely not self-intersecting, so that shouldn't be an issue. Alright. Oh, I can't think about this too much. We'll worry about it tomorrow. Yeah, I'll properly debug that failing test case tomorrow, because I need to actually draw a whole graph, draw a whole diagram, because you can't rely on this. They're using computer graphics way. I could switch to using computer graphics. Maybe I should. Maybe that's the easier way. Then my diagram will match theirs. They're doing J increases, Y increases in the downwards direction, and I'm doing it increases in the upwards direction. So the coordinates are slightly different. Yeah, we could switch to rows and columns. Tree the hex hog triple trouble tomorrow. Yeah, you know how much I love hex hog. Speaking of which, are there any more hex hog races coming up? There was only gonna be one, wasn't there? And that was the shuffler, and that's done. All right. Next season. Yeah. I suppose I can maybe raid somebody who's doing this problem. I don't like raiding when I haven't solved the problem. I think I haven't earned my reward. Alright, I won't bother today. Okay, that's it. I think closing the browser just crashed the stream, although my mic is still going through, but everything has just crashed. Alright, never mind. See you next time. Bye bye.